parameters too. So hopefully your graph is all good. And now we're going to start analyzing our graph to get more information. The first thing we're going to do, as it's asked, is calculate the slope of the line on this paper. Well, let's do that. All right, once again, to find the slope, we're going to need to pick 2 good points. Not data points from your data table, but 2 points on the line of best fit that you drew. I found 2 points that I like. I like this one because it's at the X and Y cross section, and I like this one too. So let me actually figure out what those guys are. When looking at the bottom here, I have 5 lines between 0.2 seconds. So if I took 0.2, divided by 5, that gives me 0.04 seconds is what each little hash mark represents. So that means this dot right here is actually 0.04 seconds over, and upwise it's 16, 17, 18. It's 18 up. So that's my units and coordinates for that. For this guy, we're going to have to calculate and see. It is at 1 over from 0.2, so that is going to be 0.24 seconds, and it's right on a big hash mark here, which is at 20. So now that I've picked 2 coordinates off of my line of best fit, notice I didn't use any of my data points. All right, once we use our data points, we use it to get a line of best fit. After that, we no longer care about the data points. So now it just becomes slope time. I'm going to take my y's and subtract them and divide it by my x's subtracted. So I'll start with 20 minus 18. Those are my y's. And then I'll take 0.24, which is my x, minus 0.04, which is my other x. And I'll throw that in my calc. Through my calc, I get 2 over 0.2, which when I throw that in my calculator, I end up getting a total of 10. But now remember, for slope, it's not just a matter of a number, but there's also a unit involved as well. Since the y-axis is in centimeters per second, and the time is in seconds, I really did centimeters per second divided by seconds, which really ends up becoming centimeters per second squared. So that would be my units for my slope. You go ahead and find the slope of your line, but your units should be the same. They should end up being centimeters per second squared. And though we haven't learned about that yet, you're going to find that that's actually the units for acceleration, meaning if anything speeds up, that's the units it would be in. But all right, go ahead and look at your graph, look with your partners, make sure you can find the slope of your graph and calculate it correctly. All right, so hopefully you found the slope and you're feeling confident with that. Letter B now talks about what quantity is most likely represented by the units from the slope on the interval velocity versus time graph. Remember, I said centimeters per second squared is the units. So look that up, Google it, whatever. What would this be units for? What quantity? And by quantity, we don't mean specific number. We mean an idea that we might learn about in class. Remember, we haven't learned about this one yet, so use your unit analysis to help you figure it out. Hopefully you figured that out. And moving forward, we need to now calculate the area under the trend line on the graph that you've created. So let's do that. Let's start breaking that down and using our triangles and squares to calculate the area. To find the area underneath the graph, we need to break this down. So I'm going to draw a line straight down from the edge of the data. So that goes to 1 second. All right, but since this is not a straight perfect line across horizontally, I'm going to break this into 2 easy pieces, a triangle and a rectangle. Now we know the area of a rectangle is just length times width. And we know that the area of a triangle is just 1/2 base times height. So let's calculate the area. First, let's look at the big rectangle. For its length, simple, it's 1 whole second. So I'm going to have 1 second times the width. The width is however high this thing is right here, which looks like it's just below the 17 mark. or I should say just below the 18 mark. So probably this one is the height is about 17.8. So 1 second times 17.8, and the units for that is centimeters per second. When you multiply 1 second times 17.8, you end up getting 17.8. But what are the units? Well, if you take centimeters per second times second, the seconds cancel, and you're left with centimeters. So the area of the rectangle is 17.8 centimeters. Remember, it's not centimeters like on your paper, it just represents centimeters because of the units. Now that's the rectangle. Let's figure out the base and height of the triangle. All right, so the height of the triangle goes from 17.8 all the way up to, let's see, what does this go up to? 26, 27, 28. It's about 27 and a half. 27.5 is the height. All right, so if we take the difference between the two, I throw that in the calculator. 27.5 minus 17.8. All right, the height is 9.7. And since it's on the y-axis, that's centimeters per second. Okay, now what about the width of the triangle? Well, the width is just from here to here, which is 1 second. So I'm going to take, let me get red here, 1 second times 9.7 centimeters per second. But don't forget, for a triangle, it's 1/2 base times height. So I'm going to take my 1/2 times 1 second times 9.7 centimeters per second, and I end up getting about 4.85. Now again, look at the units. You're multiplying centimeters per second times seconds. Seconds cancel out, you're left with only centimeters for your answer. So you now just found the area inside the triangle. You already found the area inside the rectangle. Add those two guys up. So let me change my color here. It's going to be 4.85 centimeters for me plus 17.8 centimeters. Add those guys up, and you end up getting about 22.65, and the units are centimeters. So what does that mean? All right, we'll have to think about that. Let's move forward with after we found our area. So my area under the graph ended up being 22.65 centimeters. Now the question is, for D, what quantity does the area under that velocity versus time graph actually represent? Well, what is actually only measured in centimeters in this lab? All right, think about it. What, not quantity, meaning not number, but what idea from physics have we learned so far that we can measure in centimeters? That's the quantity you just figured out. You figured out that from your graph, so write that down. As for E, what type of relationship is found on this graph? With perfect data, theoretically, that car's velocity should never be changing, right? It should be perfect. So theoretically, we should see no relationship whatsoever. It was just nice, uniform motion. But mine was curved up a little bit, and it looked like a little bit of a linear relationship. But overall, it really shouldn't have had much slope, if any, whatsoever. We can't avoid that, though. Sometimes they're just experimental error. That's just the way it is. And speaking of experimental error, that's why we look at percent error. Now, finding percent error, you have to figure out what is your accepted value and your experimental value. And we know percent error is accepted minus experimental over accepted times 100%. As it states, your accepted value is the total displacement after 1 second from your actual data table. And the experimental value, the E, is the area from underneath your velocity time graph, which we just calculated. So you have these two variables, or values I should say. You can plug them in, chug out your answer, and see what percent off you are. Compare that to your other lab partners, because they'll have slightly different error because they drew their line of best fit probably slightly different than you. They averaged out as best they could. But there's error involved with that as well if we're not using a computer. And last but not least, after you've done all that and analyzed your graphs for uniform motion, the take-home message here is, what did we actually learn? So, using 5 sentences, please show the relationships between distance, displacement, speed, velocity, and acceleration. And please underline them when you give your explanation. But what did you learn from them and how they're related between graphs? Again, to recap, you graphed displacement versus time, kind of looked like this, and you graphed velocity versus time, which looked more or less like this. How do all these things relate to each other? Write in a nice, well-written 5-sentence paragraph, and you should be all set. All right? Best of luck. Thanks for doing the lab.